Yeah, it's a great question. Well, so we started getting all the materials into the field. So we were working at Smith in the Center for Design and Fabrication, and it was basically a big machine shop, and it was empty because Smith at that point, no one was on campus. We actually got special permission to be in there. So we had the run of the whole machine shop, and we had a whole bench top with all of our parts, and we would bring the parts in, and we could start to pull things together. What was tricky about it is, ideally, in an ideal setting, we would have tested the entire airflow, and then we would have tested all of the electronics, and then we would have added in the user interface. But because our system was not solely mechanical or a solely electrical, we had to test more of those pieces together. So for instance, we wanted to test whether air could go through the solenoid valves and into the mixing chamber and then through the next solenoid valve. But to do that, we had to wire up the solenoid valves and then attach them to a program that would encode them to turn on and off. And then we had to wire up a sensor to know whether things were actually, whether we were getting flow and what kind of pressures we were getting. So we ended up having to really do a lot of the wiring and a lot of the combining of the different subsystems together before we could do full testing. One thing that we did do, I'd say what we really ended up doing, rather than dividing up the airflow and the electrical, is we divided it into sort of phases of the design. So the first phase is just having air and oxygen come into the mixing chamber. And so we tested that piece and got that to work. And then we added on a proportional solenoid valve. That's the one that allows a sort of gradual opening and closing. And we did a lot of troubleshooting with that, because that's really the heart of this ventilator. It's where all the controls are built in. And we had to test that. So we got to the point where we had air coming from our compressed air tank, or from the wall compressed air source, all the way through the first solenoid valves, the mixing chamber, the proportional solenoid valve, and coming out. And we could see it coming. We call that whole line the inspiratory line, because that's the line that's going into the patient's lungs. And we didn't attach it to any sort of balloon or anything, but I put a little piece of toilet paper on the end of a tube, and you could watch the toilet paper go up and down. Like, okay, we're getting that much. But to then have the system go all the way through to the balloon, which is representing the patient's lungs, and then out from the balloon and out from the system, we had to then engage the fourth solenoid valve. And so we had to wire that up. But the trick that we faced is that we had some power management issues, in that we had ordered a power adapter that would have allowed us the appropriate voltage and current capabilities to be able to run all the solenoid valves at once. But the part that we had gotten from McMaster Carr, it turned out they sent us the wrong part, and it didn't have the right plug on it for what we needed. So we were making do with a small power source in the lab that we were working with, but it didn't have a high enough current rating to be able to run all the solenoid valves at once. So we actually, because we were limited by that, we couldn't run all the solenoid valves at once. We could either run the first two with the third, or we could run the third with the fourth. But the fourth one was a really, really high current draw. And so until we figured out the power system and got that capable enough, we couldn't run the whole system. So I remember it was a really big day when we finally were able, we got the right adapter. It was a bit of a scramble. Where else can we get this adapter from, and how quickly can we get it here? And in the end, I think we ended up with about 3 different adapters, just because we wanted to have some redundancy, and because we weren't sure which ones were going to arrive at which time. And when we finally got one that had enough juice in it to run the whole system at once, then we were able to turn all the solenoid valves on and off, and we could then run air through the entire system. And that was the day that we saw the balloon, inflate and deflate, and that was like, okay, we finally got it. We really have the whole system running here. Except that was the whole sort of pneumatic system, but we still didn't have all of the user interface, which was going to be controlling all of the electronics. And that was another whole piece that we put on. And then ultimately a later piece that we didn't even get to was to build the entire enclosure. So for a while we were working just, on a very small tray, or a very flat tray on our test bench, but we realized we needed something to be able to move this and have it be better enclosed. And so one of our team members designed and built it's essentially like a large breakfast tray with handles on the side. So it contains the whole device. And we realized that was very useful because we could pick it up, we could move it, but we could still access it from the top. It didn't have a top on it. So we could get in there and we could change parts out and we can move parts around. And that was really useful. So we, in the end, because of our time frame, never actually built the full enclosure, the full surround enclosure that we had in CAD, partly because we were still doing a lot of testing and we were still refining the design and we wanted to be able to access all the different parts. But that would be yet another subsystem that we could have put on going forward. So I guess in answer to your question, yes, we did design it and build it by subsystems, but they weren't the same subsystems that we had thought we would do when we started putting it together.